Okay, we're 5 videos into vector calculus. We're finally going to get to some of the meat and potatoes of vector calculus. We'll start out with differential calculus, and the first subject is the gradient. So what is the gradient? We have a function, a scalar function. Here's what we call the gradient of f. There's also this symbolic notation, this inverted delta. The operation we do to that function. What it means is you take the partial derivative of this function with respect to each of its variables. You make a vector out of it. So you had a scalar function going in and a vector function coming out. So here's an example. Let's say here is your scalar function. Scalar function means you put in your x, y, and z, and you get a number out, not a vector. So its gradient means, well, let's take the partial derivative of this guy with respect to each of its variables. With respect to x, it's this. With respect to y, it's this. With respect to z, it's this. And we put all them in a vector. The x thing goes to the x, the y thing goes to the y, and the z thing goes to the z. That's how you take a derivative. To take a gradient. We're going to discuss 3 different interpretations or uses of the gradient. The first will be the direction of steepest ascent, meaning the direction in which this f function increases the fastest. Before we get there, we have to talk about the directional derivative. I can draw it if I have a scalar function of just 2 variables, x and y. That function becomes a surface up here in 3 dimensions. For every coordinate point x in the xy plane, I get a value for the function. And all values would form a plane, right? Well, assuming it's continuous. Some kind of surface, not a plane, I mean surface. As you go from one point to another in xy space, in variable space, you go up or down or something along this surface. So there would be a slope. Now, if you wanted to know what that slope was in each cardinal or ordinal direction, say in the x direction, you would just take the partial with respect to x. If you want to know what is in the y direction, you'd take the partial with respect to y. What is it in respect to just any direction you pick? And I'll say that direction is given by a unit vector u. So what is the slope of this surface at a point in a direction you give it? That's called the directional derivative. Here is its notation. Direction of the function f, or the directional derivative of the function f in the direction of u, which is a unit vector. Well, it turns out to be the gradient dotted with that u. If you want the derivation of that, email me and I'll send you my written notes. I didn't think the derivation was quite worth putting in. So if you're given a more general direction, it's not a unit vector, you just need to normalize it before you take the dot. Here's an example. Find the directional derivative of this given function at the given point in the given direction. So we need all 3 of those things: function, a point, and a direction. First thing you got to do is take the gradient, which means take all those partials. So we take the partial of this with respect to x, you're going to get 2x times the rest of it. Right? With respect to y, you're going to get 2y times the rest, etc. Assuming you can take derivatives, partial derivatives. which we covered in a previous video. So now that you have that, you have to plug in the values for x, y, and z. So wherever there's an x, I put a 1. Wherever there's a y, I put -1. Wherever there's z, a 1. A little tedious arithmetic here, but here I get a vector. What is u? U, well, it's not u yet. They gave us a direction, 0, 3, 3. I need to normalize that before I take the dot product. That means divide by the magnitude. The magnitude is 3 squared plus 3 squared, 9 plus 9. Here is the u I need to dot. Simplify. So the directional derivative, what we were asked to find, is this dot product. This vector dotted with this u. And you can take a dot product by now, and there's the answer. So it's just kind of plug and chug if you know what to do. Steps. Everything by steps. And so that's a directional derivative. What would be the direction where the function increases the fastest, or the steepest ascent? And what is the rate of that? Well, here's the directional derivative. We want the u where it's increasing the fastest. Remember, there's another form of a dot product. It's the product of the magnitude of the two things being dotted, the two vectors being dotted, times the cosine of the angle between them. We'll use a unit vector, so that's just 1. So here's what we want to maximize. This is maximized when cosine of theta equals 1 or theta equals 0, and 0 is the angle between the two things. Two things are u and the gradient. So the direction where it's increasing the fastest is in the direction of the gradient. I just talked my way through that little derivation, assuming you believe this is the directional derivative. So the gradient itself is the direction of steepest ascent, or the direction in which the function f is increasing the fastest. It's a direction in your variable space. In this picture, the direction is in the xy plane. If it were in this if this were the u direction where it's increasing fastest, means this surface is increasing fastest at this point in that direction, up fastest. And the exact opposite is where it's decreasing the fastest, and the rate is the magnitude of the gradient. We have fairly easy methods to calculate these things: the direction of steepest ascent and the rate of that. And if that dot product is 0, that means the function is neither increasing nor decreasing in that direction. So let's do some examples. Find the direction in which this given function increases most rapidly at the indicated point, and find the rate. Direction is a vector. The rate is a scalar. I used to get irritated when students would give me the wrong form and give me a vector for a rate or a scalar for a direction. At least get the form correct. So here's the function. Find its gradient. It'll be 2x. By the way, you got to take the partial over all terms. 2x plus 4z, the x part. The y part is 2z squared. The part is going to be 4x plus 4yz. Now evaluate it at the point given. So I plug in 1 for x, 2 for y, and -1 for z. Add arithmetic, get this vector. This is the direction in which f increases the fastest. And the rate is the magnitude of this. It would be 4, the square root of 4 plus 4 plus 4. Now, actually, any direction, I could have said 1 minus 1, 2. That would be a legitimate direction. But to get the rate, you need to use the numbers you got when you plugged in the point to the gradient. You know, any vector that's parallel to this vector is a legitimate direction in which f increases the fastest. But if they don't ask for a unit vector or anything else, here's your answer. But as for a unit vector, you would need to normalize this, which would mean just divided by this. Let's do another example. Consider the scalar function and a point. Okay, what's the maximum rate of increase of f at the point? We're asking for a rate. The answer is a scalar. What is the rate of increase in the direction from the origin through P? That's going to be a directional derivative. And find a direction in the xy plane in which f is neither increasing nor decreasing. These are actually kind of related calculations. Go first, calculate the gradient. That's going to be, what's it going to be? 4x plus 1/2 y squared in the x direction, or in the x component. For y, what am I going to have? 2, I'll have xy plus z. Got to go through all terms. I almost just did it wrong. And for the z, there's no z there, no z there, so here's just 1. So there's the gradient. At the given point, plug in the numbers, and here is the gradient at the point. The rate, then, is the magnitude of this. Will be square root of 36 plus 9 plus 4. Turns out to be a nice whole number 7. That's the answer to part A. What's the rate of increase from the origin through P at the point P? Well, we already had this calculated. So now all we need to do is dot it with the direction they gave us. And that's from origin through P, which just means 1, 2, 1. I need to normalize that vector, which will be divided by square root of 1 plus 4 plus 1. Okay? Do that bit of arithmetic, and here is the answer to part B. Rate of increase of f in a given direction. This answer must never be more than this answer. Can't be more than the maximum. And finally, this direction of A, we explicitly say, here's what your A vector looks like. Some number in the x and y places in 0 and z. In which it's neither increasing nor decreasing. Key there is to look where that dot product equals 0. Here's what we want to happen. The gradient of f at that point was 632. 632 dotted with the vector we're looking for has to be 0. That gives you a relationship between A1 and A2. So any vector parallel to 1 minus 2, 0 would work. Okay. So that's it for gradient as gradient and directional derivative, and the interpretation of gradient as direction of steepest ascent. The next thing we'll get to is another interpretation of the gradient.